Hello and welcome. In this video, we're going to take a look at the derivatives of inverse trigonometric functions. And there's a couple things that we need to know first before we can kind of investigate those derivatives. We need to know how to use the technique of implicit differentiation because, well, an inverse function can always be written in the opposite way. If we have y equals inverse sine of x, then x is equal to sine y, for instance. And then we can apply implicit differentiation. And then also we need some other properties about trigonometric functions, such as some identities. So, see how we can put all those pieces together, find the derivative of, let's say, arcsine. We kind of want to be able to get all 6 inverse trigonometric function derivatives. Arcsine is just maybe the easiest one to take a look at first. But the technique that we use to find the derivative of arcsine x would be very similar to finding the derivatives of arc cosine, arc tangent, cosecant, secant, or arc cotangent, any one of the 6 major trigonometric ratios. Oh, let's start off with arcsine. Now, if we ever have an equation of the form y equals arc sine x, now, of course, feel free to use sine to the -1 notation. Inverse sine can be written either way. But I like to use arcsine because it really doesn't have anything to do with exponents, generally speaking. If we write y equal arcsine x, then of course, by definition of inverses, we must have that sine of y is equal to x. Once we have this written out with just sine y, we already know the derivative of sine. Now, if we want to find dy dx here, we're going to have to use the technique of implicit differentiation. We'll have to take the derivative of both sides with respect to x. On the left-hand side, since we have a function of y, and we're treating y as this implicit function of x, we're going to have to use the chain rule here. The derivative of the sine function with respect to y is going to be cosine of y, and then we must multiply by the derivative of y with respect to x. On the right-hand side of this equation, we simply have a function of x, and the derivative of x with respect to itself would just be 1. And it's pretty easy to solve for dy by dx. The derivative of dy by dx is 1 over cosine y. Now, we could probably just stop right here, except for the fact that, well, we started off with y being explicitly written as a function of x. Y was equal to the arcsine function of x. And now our derivative, dy by dx, is actually a function of y. And so it feels backwards here. If we know a value of x, we should be able to find y. And if we know a value of x, we should be able to find y prime, the slope. We should be able to do that if it is explicitly written as a function. So we need to continue this process of how do we get this cosine y written in the form of a function of x? Well, and this is where we need to rely on some information about trigonometric functions. And we can either use some identities, or we can simply look at sines and cosines as being ratios of a right angle triangle. There's a couple different techniques we can look at. Let's start by thinking about definitions of sine and cosine in terms of right angle triangles. From the moment that we wrote down sine y equals x, then we can actually write that as a triangle with 2 sides being the ratio of x. Sine y equals x, or if you wanted to make this a fraction, sine y is equal to x over 1, would be the ratio of the opposite side from the angle y and the hypotenuse. So our angle is y, our opposite side is x, and the hypotenuse is 1. And by looking at this triangle, now that the sides are given in terms of x's, we should be able to state the value cosine y in terms of x's. Cosine of y is a different ratio. It's going to be the adjacent side divided by the hypotenuse. And we already know the hypotenuse has a length of 1. We just need to find out what the length of the adjacent side is. And that can be done using Pythagorean's theorem. The adjacent side squared plus x squared must equal 1 squared. That means that the adjacent side must be the square root of the hypotenuse squared minus the opposite side squared. So the remaining side has a length of 1 minus x squared, all square rooted. And that means that cosine y can be written as the square root of 1 minus x squared, all square rooted, as the adjacent, divided by the hypotenuse, which is 1. And of course, since it's just over 1, cosine y is simply just the expression root of 1 minus x squared. And so we can make the replacement cosine y equals square root of 1 minus x squared. Now this is just using a right triangle approach, and there is another option that we can use here. And I'll provide both options in this video so that you may find that one is a little bit more straightforward to follow than the other. Using a different approach, an identity is useful here, and it is one of the Pythagorean identities. In this case, it would be one of the identities that involves cosine, and the Pythagorean identity that involves cosine is sine squared theta plus cosine squared theta equals 1. Let's just change that so that we actually involve the variable y. Sine squared y plus cosine squared y is equal to 1. Now, once again, we have to go back to this blue starred equation. Sine of y is simply equal to x. And that means that sine of y can be replaced here with x in this Pythagorean identity. X squared plus cosine squared y equals 1. And if we're trying to make a replacement in dy by dx here, if we want to get rid of this cosine y and replace that with an expression for x, then we can rearrange this identity now. Cosine squared y is 1 minus x squared, and so cosine of y can be replaced with the square root of 1 minus x squared. Once again, it's the exact same replacement using a different approach. And both of these are useful. You may find that right triangles are a little bit easier to remember if you can remember opposite, adjacent, and hypotenuse and the common ratios and things like SOHCAHTOA for sine, cosine, and tangent. The identity approach can be very useful, but you'll also have to use the Pythagorean identities occasionally for things like secant and tangent, cosecant and cotangent, and perhaps those are a little bit trickier to remember in some circumstances. Either way, once we've got one of those two approaches mastered, then we can see that we can replace cosine y in the derivative here with the expression root 1 minus x squared. Now that means that the derivative dy by dx is simply 1 over the square root of 1 minus x squared, and since y was equal to arc sine x, that means that the derivative of arc sine x is equal to 1 over the square root of 1 minus x squared. Now what's a little bit interesting here is whether you're using the right triangle approach or you're using the identity approach, the Pythagorean identity is used one way or another. Either you're using the a squared plus b squared equals c squared identity to find the third side of that right angled triangle, or you're using the Pythagorean identity in terms of the trigonometric ratios, like sine squared x plus cos squared x equals 1. You have to use it either way. So whatever you find easiest to use. Now, I'll leave this as an exercise, but see if you can now apply the same technique for finding the derivatives of the other 5 inverse trigonometric functions. And I'll provide those answers here for you. And here are the other remaining derivatives of inverse trigonometric functions. And you'll notice that in the case of arc sine, arc cosine, and arc secant and arc cosecant, that it's not differentiable everywhere. There are places such as when x is equal to plus or minus 1, or when x is equal to 0, where the functions are not differentiable. But the derivative of arc tangent is a very nice looking function actually, and it's going to be quite useful in integral calculus. It definitely comes up fairly frequently, this 1 over 1 plus x squared. Now remember, you'll need to know a couple other identities if you're going to try to prove all of these derivatives. If you want to use the identities, then you'll have to know the 3 different variations of the Pythagorean identities. Otherwise, just stick to triangles. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent, with cosecant, secant, and cotangent simply just being the reciprocals. And there we go. Now that we've got implicit differentiation behind us, it unlocks the doors to being able to find derivatives of inverse functions like these ones. Thanks for watching. I'll see you in the next video.